right. Welcome to our third lecture in our fall 2024 Saturday Physics for Everyone. I'm so glad to see all of you on this crisp morning. My name is Irene, and I am the coordinator of undergraduate recruiting, research, and placement here in the physics department. So if there are any prospective high school students who are interested in learning more about our physics majors, you're welcome to come and talk to me. But this Saturday Physics for Everyone is our public lecture series, giving our faculty an opportunity to talk about their research and for all of you to learn what's all is going on. So we have Professor Kirk Barrow, who I'll introduce in a minute, here for us today. And we do have 3 additional lectures still coming up this fall. If you'd like to get on our email list, we have a QR code, or you can sign up on our paper sign up to learn to get emails from me about the upcoming events. So, without further ado, I will introduce our speaker for today. So, Kirk Barrow is an assistant professor and theoretical physicist in our astronomy department. He received a Master's of Science in Aerospace Engineering and a PhD in physics from Georgia Institution of Technology. After graduating, he was a Pro-Rat Fellow at Stanford University and shortly a Hubble Fellow at Harvard University, as well as a visiting professor at the University of Tokyo, very cool, before he came to UIUC in 2022. His research is in the formation of galaxies in the young universe, with a particular interest in making predictions for the James Webb Space Telescope. So please join me in welcoming Professor Kirk Barrow.
I just wanted to start by thank you so much for inviting me and organizing this wonderful event. I'm an astronomy professor, not a physics professor. And so I'm really, really interested in how galaxies look in the early universe. And I do that by simulating galaxies in a large simulation of the universe. So I'm gonna go and do something a little unconventional, but I always start my talks by introducing the people who work with me. But that's not the unconventional part. But this is my research group. It evolves over the years. I've only been here for 2 years, but it changes and more people get added and some people graduate. But these are the people who are working with me as of last fall and spring. And some of their work features a little bit in my talk, but if you want to learn more about any one of these topics, find these people and find their talks. I think they have really interesting things to say. I'm really, really proud of them. All right, so here's the unconventional part. So usually what you do in these talks is that you talk about some subject that's related to your research, and you go into some amount of detail, and you explain it as best you can. What I'm going to do is I'm going to tell a story about the history of the universe, starting from the beginning, the Big Bang, and going through and integrating my research as we go and tell that story, because that's what my research is about telling the story of how the universe became what it is. So we'll start with the first million years of the universe. So the universe is expanding, and if you ask the question, why is the universe expanding? That's a question for a lot of theory. There are a lot of theories for why the universe is expanding, but we know at the very least it started expanding, and that expansion started with what we call a Big Bang. And in that very short period of time right after the Big Bang, the universe expanded very quickly. It expanded many times its initial size. And how we know that is because the universe we have right now is what we call flat. It looks the same in every single direction, which means that if there was any differences anywhere, they got smoothed out by it expanding extremely fast. So there's many different sort of pieces of evidence that the universe expanded very quickly in that very first piece of time. Like there's no magnetic monopoles or things like that, but that's not where my research goes. So let's go a couple minutes later to what we call Big Bang nucleosynthesis. So this is the point of the universe where the universe is now big enough that all the energy in the universe is now cool enough that we can form atoms. So Instead of being a big soup of energy, now we have protons and neutrons and we create atoms. And we can see the first hydrogen and helium forming in the universe. And as the universe continues to expand, it continues to cool, and we create a specific ratio of hydrogen to helium based on how quickly the universe expands and the temperature of the universe. So we know that at the very beginning, the universe was 25% helium and 75% hydrogen. All right? There's a little bit of lithium, but that kind of decayed very quickly. And the evidence we have of that is we can observe that ratio. We can observe that ratio going back in time as well. All right, so that was the first few minutes. Now we have 300,000 years after the Big Bang, and the universe continues to cool. So it's still a hot soup, but at this point, all of the light inside of the hot universe is trapped. When you have really, really hot atoms, what happens is that light will bounce between the really hot plasma and it'll get trapped, kind of like how light is actually trapped inside the sun until it can reach the surface. But once the universe cools enough, the electrons and the protons can find each other and no longer is light trapped, and then all of the light in the universe at one point in time is released. And that light being released all at once gives a glow that we can still see today. We call that the cosmic microwave background. So there's a background light in every direction. That's just an echo of this one point in time, 300,000 years after the Big Bang. And I wanted to emphasize that if you have any questions or thoughts, please interrupt me and ask them. I'm happy to, I'm a professor, I like to answer questions. But yeah, so here we are, first million years. Now, this is where we start our simulations. So all of that information that we get from the cosmic microwave background gives us an echo of a very early time in the universe and gives us everything that we know about that point in time and allows us to use that as a starting time for our simulation. So it's really nice to have some piece of evidence so you can start with the initial conditions, we call them, and then use simulations to propagate them forward. So this is how we create a cosmological simulation. So here's the recipe. First, we start with a box. And in that box, we put all the matter that we think is in the universe. And that comes in two flavors. One is dark matter, and the other is what we call baryons. So baryons includes all of the atoms, all of the things that we think of as normal matter. So this is baryons in cosmological speak. It's not actually baryons. That's what we call it. And then we have dark matter, which we are still trying to figure out what that is, but we know it's a large fraction of the mass of the universe. Yeah?
Do you have opinion what dark matter is?
Well, the consensus opinion is that the way the dark matter seems to act on a large scale is follows what we call the cold dark matter theory. So it has not been proven with an actual particle, but the way that we see galaxies forming, their distribution seems to bear out that dark matter is this cold, somewhat massive particle that doesn't interact with anything except through gravity. But that can't be proven until we can hold some in our hand and look at it and study it, and we haven't been able to do that yet. So I have an open mind. Yeah.
For seeing the real nature, real structure of life. So I had this answer for this gentleman, and I developed that experiment for 10 years. I spent my own money for building that experiment, which shows the real nature of life. And challenge both you, Professor, and the gentleman there to try to look at this case. Thank you.
Okay. Yeah, I don't work on discovering dark matter or the real nature of light. The gentleman says that he's created an experiment to study the real nature of light, and he has unique, I would say, results, and he would challenge his results against the field. And I have an open mind, but but at the moment we're assuming that dark matter is something that is cold and has some mass. So we have this box of dark matter and baryons, and initially in the universe, everything is pretty uniform, except tiny little slight perturbations. So like you move something a little bit, or you increase its velocity just a tiny bit, and that's the initial state of the universe. And then, from there, we apply gravity. So we know gravity exists, and that means that if you have an area of the universe that's slightly more dense than another area, then we expect gravity to bring it together. And then we apply what we call hydrodynamics. So this is what happens when baryons interact with each other, like they create friction, they create shocks and things like that, so that's hydrodynamics. And then we apply the fact that the universe is expanding. So we do this in reverse. That is, we keep the box the same size and we shrink everything in the middle of it. This turns out to be mathematically the same thing. But it just keeps our coordinates from 0 to 1 at all times. And then the next step is when things get dense enough, when gravity brings together close enough, then you form stars. And in the simulation where we have the right conditions for star formation, we add a star. And when we have stars, stars radiate. They add energy to the universe. They're big fusion boxes, and they are sort of the only source of new energy to the universe that is supposed to be expanding and cooling over time for the initial universe. So we add stars, and then the other source of energy might be accretion to black holes. So we have to add black holes where the conditions for black hole formation are met. So this is the simple recipe for a basic simulation of the universe. We have gravity, hydrodynamics, cosmological expansion, stars, radiation, black holes. And we started all with the CMB information. Question?
Does dark energy influence that expansion?
It absolutely does. Dark energy is something that comes more into play in the later universe. So if we're talking about the first 150 million years, which is what we are doing right now, it actually doesn't matter too much. Dark energy has this quality where it's always the same density over all time. So it turns out in the early universe, all the matter and stuff is much more dense and has a much bigger effect on the expansion of the universe. We call it the matter-dominated era. All right, so we started at the where all the light was escaped and the universe was cooling, and then we go into 150 million or so year period where there are no stars yet. So it takes time for gravity to do its work, and so for 150 million years, there's no light source anywhere in the universe. We call this the dark ages. And during these dark ages, we're collapsing into what we call structure. So the things that will become galaxies are slowly coming together. And we can simulate that change. And that part of the simulation is easy because nothing is in there except low density matter coming together under gravity. And when these pieces come together, so this is on the left, you have these particles. So we simulate dark matter and matter with particles, or similar with fields, but these are particles. And this is what a raw map looks like. And in the simulation, this is just data. And if I want to tell you there's a galaxy in the simulation doesn't tell me there's a galaxy, it just has a bunch of particles somewhere. So one of the things that we do is that we take this map of particles, maybe trillions of particles, how many ever I can fit in a computer, and I figure out where the galaxies are. So this requires an algorithm that finds clusters of particles that are bound together, but you need to go through trillions and trillions of particles. So it takes a lot of computational energy and you have to be extremely efficient. So this has been something we've been able to do for as long as there have been cosmological simulations, but we've made them better and more efficient in our current research. But that just addresses the first step. All right, so we don't have any evidence of what happens in the dark ages. And this is important because there is no light. There's nothing we can see about it. Even if we look at the earliest galaxy we've ever seen, this is way after this point in time, even of JWST. So this is the first period of the universe where we have no evidence. We never have direct evidence of this period because there's nothing our telescopes can see. And then, at about 150 million years, you finally form the first, what we call protostellar cores, so what will become stars. And it all starts with a gas cloud. So gas in astronomy talk means that hydrogen and helium, so it's floating around in space, and it's coming together under gravity and it forms this cloud. And this cloud collapses because it slowly cools. So a hot thing expands, a cool thing collapses, and it forms one of three different cases. So it can all collapse into one object, like a black hole. So it all comes together and collapses, and it collapses under its own gravity, and it becomes a singularity, becomes a big black hole. It could collapse into big stars with an average mass of something like 40 times the mass of the sun, or it could collapse into smaller stars that are a lot like our sun, so something with the average mass of the sun. And the difference between these three cases, starting with the same size gas cloud, is chemistry. So the very first stars that are forming are made out of just hydrogen and helium. After you form a star, fusion inside that star makes heavier elements, or changes the ratio of elements as well. And it turns out the more complicated your chemistry is, the more complicated the cloud is. And the more complicated the cloud is, the more complicated the thing the cloud collapses into, because it doesn't collapse uniformly. So the first clouds that collapse have the greatest chance of creating black holes or creating really large stars. But a couple generations later, these stars will add chemistry. Then you form the kind of stars that we have today. So this is sort of the generations of stars. And this is captured in our simulations.
Question?
Yes?
How do you assign time to this collection of ideas? You're talking about this through time. Can you discuss that?
How do you mean, how do I assign time?
Now we're at 150 million years out.
Mm-hmm.
I mean, you're wondering where that element.
Sure, sure. Well, we're helped during the Dark Ages by the fact that we know how they started, because there's light from how they started, and the fact that we know enough about physics that if it's simple, we can just apply physics and propagate it forward and figure out how long it takes for things to form. So I'll admit to you that each simulation starts star formation at a little bit of a different time. So when the first star forms is actually still unknown because we haven't seen the first star. But we know that it's sometime around 150 million years ago. And there's a slide that I took out because I had to pick what was in here that shows evidence for when the first stars formed. It's called the edges result. I don't have a plot of it here. But we do have some sort of upper bound on when it starts. If that answers your question. Okay. So what happens when the gas cools and collapses into these cores? You get light. You finally get light again. You get the first galaxies, stars, and black holes. And this is simulated galaxy on the left. This is a proto-galaxy. And on the right is actually a simulated formation of a black hole that I did in 2 different research projects. And they kind of look similar in a way because this is kind of how this structure comes together in the simulations. All right. Now we have energy from the sun, and this energy heats up the universe, and it separates the electrons from the protons. And this period is called reionization. So when you separate an electron and a proton, they become ions, they have different charges, they move apart, so the universe is cold, and then all the stellar light heats it up, and this process takes unto 1 billion years after the Big Bang. So this era is a really important place in the universe because this is where the first stars and galaxies and black holes form. And until JBST, we had very little direct evidence of this place. So this is a very active area of research. Now, the James Webb Space Telescope has been up there for a couple years now. So this is results from the JADES collaboration, and it's it was the first, the highest, sorry, let me put this into the right units. The earliest galaxies that we've seen in the first round of data from JBST. So these Z numbers relate to time in some way, but the higher they are, the closer they are to the Big Bang. So in the first few 100 million years of the universe, we've finally seen the first galaxies, but we haven't seen the first stars yet. So we need to go further with better telescopes and more techniques to actually see the formation of a galaxy. So these are young galaxies, but they're not the formation of galaxies yet. But we do know at least that there are galaxies at this point in time, which is a win. All right. Now, this is a map of the furthest identified galaxy candidate with the Big Bang. And on the bottom axis, we have time. Redshift is on the top axis. And you can kind of see in the map how galaxies sort of look and evolve. So on the left side, we have what galaxies look like today. And on the right side, we just have bubbles of hot space and those proto-galaxies that I showed you before. So I just wanted to put this all out on a map so you can put it into context. Now, when light from these galaxies is emitted, the universe stretches and expands before the light reaches us. And that causes the light to change its frequency. We call this redshifting. It's because everything looks more red than it was. And the redshifting to the early universe is so extreme that it moves out of the visual range where the stars have most of their light into the infrared, which is why the James Webb Space Telescope is an infrared telescope. It looks at infrared frequencies. It doesn't look at visual range frequencies. And the thing about infrared light is that everything gives off infrared light. You and I give off infrared light. So one of the big challenges with the telescope was to keep it from giving off any heat, which means it needs to be kept at cryogenic temperatures, which is why it has that big sun shield, and it took an extra, I want to say 15 years to figure out. Okay. Now, this redshifting effect means that you can use the wavelength of the light that you see. So we know what stars look like, so we can see how they've been shifted to figure out when that light was emitted, as long as we know how the universe expands. All right. So getting into my simulations, this is what they might look like as I animate them in time. It's a little hard to see if the light's shining on them. But in the middle, I think, is where you'll see the most action. Stars and supernova explode, and that color is temperature, and you'll see them heat up and expand the universe. So this is the process of reionization in my simulations. On the right side is actually chemistry forming. So the yellow areas are chemically enriched. On the left side, which is harder to see, is the density, and the density just goes up in time. Okay? Yep?
Did you mention how big a computer or how much time it takes to do these simulations?
All the computers. No, so I used the Stampede supercomputer at the Texas Advanced Computing Center. It was, every now and again, it's the biggest computer that we have access to in science. It isn't exactly right now, but it takes a few months to run this on many, many, many cores. So hopefully I get something out of it, right? All right, so here is where it gets interesting. So I said there's radiation from the galaxies. So this is how I see the field of astronomy and computational cosmology, which I call my field. So we have simulations that start at the very early universe, and they run forward in time. And we have telescopes that sit here today and look back in time. And the further we look back with telescopes, the harder things are to see. And the further we run forward with simulations, the harder it is to simulate. And there's this region of overlap where we can use the simulations to improve what we know and see from the telescopes, and vice versa. So this is where we can learn from observations and simulations at the same time. So that's where I focus my research. This is an area where we can iteratively improve our knowledge of both the theory and the observations and what we're seeing. Now, in order for us to be able to compare telescopes to simulations, we can't have like trillions of particles and be like, oh, that's what the universe looks like, because that's not what telescopes see. Telescopes don't see trillions of particles, they see pretty galaxies. So we need to create those pretty galaxy pictures from the simulations. And that's what we call synthetic observations. And synthetic observations is anything that involving the light that we would simulate from galaxies. So it can be how luminous things are, images of galaxy, spectra, so that's light at different frequencies of light, what we call emission lines, so this is light that comes from chemistry. And then we can just figure out how many galaxies there are and learn something from that. So this is what Hubble Space Telescope and JVST images look like. You can actually see in the JVST image arcs and rings. Those are called Einstein rings. This comes from light bending around massive objects, and it actually causes a magnification effect, which is really great, because without magnification, there's a lot of things you can't see. And but in order for us to simulate all of these things, we need to do a little bit of physics. So if we have light from a star, it has something that looks a little like a black body, and then it hits a gas cloud. And if you look at the gas cloud, so the heat of the gas cloud will interact with the gas cloud, will change the chemistry of the gas cloud, and the gas cloud will glow. And if you look at the gas cloud from one angle, then we see lines form, where photons are emitted from different points in the chemistry. And if you look at the gas cloud from a different angle, we see gaps. So these are emission lines and absorption lines. So in our simulations, we need to do the same thing. So here's a grid to really emphasize this as a simulation. There's stars in that grid to emphasize that I don't know how to use Microsoft Photoshop or Microsoft PowerPoint as well as I could. But what happens is the light from the stars will have to go to everywhere in the simulation, interact with everywhere in the simulation, and then come to us as an observer. So that's what we need to do. So this is, as hard as it is to run this simulation in supercomputers, simulating where all the light goes is another order of magnitude harder. So this is the result. So we have a synthetic image that I'm moving in time of a proto-galaxy forming. We have a synthetic spectra in the middle, so that's wavelength versus how much light is in that wavelength. I have some emission lines on the right, which just emphasizes some of the emission lines in there. And then I have some other quantities that you can see. And I do this by looking at 8,000 different wavelengths. I trace light rays from every star to every voxel data. So these are just 3D points in space. And I do the whole photochemistry. So chemistry plus radiation equals photochemistry. So you have to solve a bunch of equations. And then I can figure out how everything looks as a function of time and orientation. Eventually, this will turn into a spiral galaxy, and then crash into another galaxy, and so forth. Okay. Which brings us to the next 2 billion years. which is what we call the cosmic morning. I say we call it. I don't know that anybody else has really called it at this, but I'll call it this. So this is where we now have created our galaxies, and they need to evolve. So they turn from these proto-galaxies into spiral galaxies. They grow, and they crash into each other. So I'll play a short piece of this simulation, which is cited here. It's not from me. It has a beautiful soundtrack. I don't know if it's going to play. It's not going to play. But this is what the simulation looks like, and it's simulating. It is playing. And this is the box of the simulation. And then all those pieces right there are galaxies. And if you zoom in, it's starting at the end of that 1 billion year period, and it's going forward for the next 2 billion years. So, yeah. Okay. And that's all the time we have for that. All right. So this part is something we have lots of evidence for, because we're no longer talking about using the most powerful telescopes to see just a few galaxies, to put in some bounds to where star formation starts. We can see these galaxies. And so now, if we've done our cosmological simulations right, then our simulation should look a lot like the universe that we see. And it does look a lot like it, which gives us a lot of, I mean, if it didn't look like that, we wouldn't even have this field. So we've made a lot of progress, and that's why we're able to talk about this, this era. Now, when I have these simulated galaxies, one thing I like to do is I like to look at every point in time. Sometimes when you make these simulations, you look at the end because you're interested in like what it looks like today, or you look at a few points in time, but I like to look at all the points in time and simulate things as a function of time. And what that means is that I need to save the state of the simulation very often, which means that I need to use a lot of storage space. So I'm a problem for the supercomputer. But I usually save the simulation every 1 million years. And this captures every nuance of star formation and radiation and all of the changes in the spectrum. And it allows me to see all the things that galactic light can do. Now, in order for me to study merging galaxies, this halo finder that I made also needs to work as a function of time. So this is the assembly of something the size of the Milky Way, and the many hundreds and hundreds of galaxies that have to crash into each other in order to create something as big as the Milky Way. So this is overall of cosmic time. So this is something fairly new, but what do we gain by looking at merging galaxies? So so when I was shortly at the University of Tokyo, a problem came up with Kashi Daiichi, where it seemed like the stars in the center of the Milky Way had too much had too many metals, so it had too much enriched chemistry compared to how old they were. So we wanted to figure out how that could be and why that could be. So I ran this simulation, and each one of those dots is a cluster of stars, and the color represents how much metal there is. So the darker colors going towards purple means not a lot of metal, and then the yellow means lots of metal. So this is what it looks like in time. So there's two galaxies. One of them is like this, and one of them is like this, and they're drawn together by gravity, and they're ripped apart, and they make one pass at each other. So this is going like this. And then they pass each other, and then something interesting happens if you look very closely. So after that pass, we see a little bit of color forming in both of them. It's a little bit more stark in the top one. And the passing of these two galaxies near each other cause stars to form so quickly that the chemistry of the entire galaxy was changed. And then they do a second pass, and this only accelerates the process. And then they finally coalesce together. And when they coalesce together, they form a galaxy, so it's going to coalesce soon. It's bouncing around there a little bit. So they form a galaxy that looks face-on like this, but the core is different than it was before for any of the two galaxies that came in. So it's a core that has lots and lots of chemistry inside of it. And this was what we thought a good explanation for why the Milky Way center looks like how it does, because we know that about 10 billion years ago, the Milky Way had a major merger with a galaxy around the same size, called the two galaxies Gaia and Enceladus, came together and formed the Milky Way. And so that might explain why these stars look like this. Okay, let me see how much time I have. A little bit of time. All right. Now let's get into astronomy. So here we have the James Webb Space Telescope, and it's very pink. I actually don't know why it's so pink in this picture. But what it has is it takes in buckets of light. So this is what we call NIRCam. So this is the one that takes some pretty pictures. And if we look at the light that's coming in, if we are using a camera, the camera is at different wavelengths, and we only have a few images of the galaxy to learn as much as we can. And sometimes the galaxies are so far away, they're just points of light. So we can't really tell much from the way it looks. We can just get points of light and how much light we're getting. So it really comes down to a handful of numbers. So in the example I have at the bottom, we get 3 numbers from 3 filters. So the F150W filter, F200W filter, and F277 filter, we get 3 numbers. And from those numbers, we try to figure out, first, where this galaxy is, how far it is away. All right, and then second, how many stars are in this galaxy? And those 2 things are what we call degenerate. So knowing how many stars there are, then you can figure out how far it is away, because you know how much light it could produce. But if you don't know how far it is away, you could have more or less stars, and it would give you the same answer. So we use these 3 numbers, or sometimes we get up to 6 numbers, depending on the galaxy. We have to learn as much as we can. So one of the things that my group is doing is we're using machine learning. So this was work that I did with my advisee, Lillian. She's at Stanford right now. And on the left, we have an estimate for the redshift. So how much light has been redshifted from the galaxy. And we have every single predictive software that's really in high usage that was used to look at this object. And there's lots of different ranges and uncertainties, but there's one that looks a little bit different. It's just a vertical line that goes up, and that's our work. So the work we did here allows us to take a very few pieces of information and get a very accurate read on how far away this galaxy is and where exactly it was in time. So this is one of the pieces of work we did with that. And then the second piece of work we did is we figured out the whole history of stars that formed in the galaxy from those few pieces of light. This is a technique we call SED fitting. So you take the spectrum of a galaxy and you match it to a model. So usually what you do is you make a bunch of toy models of, okay, stars formed at this point in time, what would it look like, and so forth. But what we have is lots and lots of simulations. We've fully simulated all the light. So all of our models are fully simulated galaxies. It takes a lot of computational resources. It warms the planet a little bit, but we finally have like a really rich data set. And the first estimate for these, there's 2 galaxies here. One that's at the top and one is the bottom. And the first estimate from the JADES collaboration, so they're the main people who look at JBST images inside of these what we call gravitational lensing, so the magnified galaxies. So the first estimate is that all the stars were 1 million years old. And problem with that estimate is that's impossible. All stars can't be less than 1 million years old. But when we applied our technique, we got these possible histories. So this is how many stars, the formation of stars over time. So for the top galaxy, we have a hump in time, a hump of star formation, and then another hump. And for the other galaxy, we have one hump of star formation like that. And we were able to estimate that the stars in one galaxy were about 100 million years old, and another galaxy is about 50 to 70 million years old. So this is something we use our simulations to predict. It's still a work in progress, but it is making changes in the field. And the reason why our results are much different than a lot of the fiducial results is because never before have the simulation people and the observational people been able to collaborate and talk in this way, because they've always been looking at different points in time. So we're rapidly evolving our techniques so we make better predictions and learn more about the universe. And going forward, my research group is going to look into a lot of these things. I'm busy teaching and doing a lot of things, but so I'll give a lot of credit to them. But we have the tools now to make faster and faster strides in our understanding of the early universe and get to the very core of why stars form the way they do, what kind of stars form the way they do, the kind of galaxies that form in the early universe, and how black holes form. And so that's all I have to say for today, except, well, I forgot this one slide. We were able to simulate the actual two galaxies using the images as well. So that's the end of that. But that's to say that there's a lot more to come. And the really exciting part of my talk, ask me in 1 year, and we'll have some really interesting things to say. Okay, thank you very much.